Yep.
Yep. So we're going to be talking about solids, and the reason we're using the Hoffman book right now is our book doesn't really do a great job at describing electronic structure, and since we're already talking about molecular orbitals, we'll move to molecular orbitals of solids. So we've talked about like how molecules behave basically in liquids and in the gas phase. What about as solids? Solids. So can anybody tell me what a solid is? Geez, this camera's freaking out.
Compact state of atoms.
What was that?
A compact state of atoms.
Yeah, that's a good one.
The kinetic energy is like almost zero.
What did you say, Maddie?
The kinetic energy is almost zero.
Yeah. So low kinetic energy. So what does that mean about the movement of the molecules then?
Minimal movement.
Yeah, minimal movement. Exactly. Another way to say this too, these systems are periodic. And what do we mean by a periodic like function or a periodic system?
As a pattern.
What's that?
It has a pattern.
Yep, it has a pattern. That pattern continues forever, right?
Yeah, it repeats.
Yep. So this is something that extends to infinity. And they have some pattern. So normally we would look at some models to talk about solids, but I'm gonna think about how to do that a bit later. For now, let's talk about the electronic states. In solids. So this is a bit different because in molecules, we have discrete states, so specific states. Discrete energy levels. Whereas in solids, what did we say solids had? Like back in lab when we were talking about carbon nanotubes, what does the electronic structure of those look like? We don't have discrete levels, we have something else. You remember what it was?
Concrete.
What was that?
Concrete energy levels.
Yeah, concrete. Yeah, I mean that's true. There's definite regions that they have, but like remember we said that they had like a continuum of states. And do you remember what we called that continuum of states?
A band.
Yep, a band. So solids have a continuum of states. Which I hate that word because there's two U's next to each other. I never think it's right, ever.
Doesn't look right.
No. Check it, probably isn't, but.
Yeah.
Okay, so what we're gonna do, we're gonna talk about like how does this band form, and we're gonna move into describing this more. We'll refresh what it means to be a band like we did in lab, and then we'll move to a more rigorous explanation. So what we're going to do, we're gonna make some MO plots. We're gonna have energy on our y-axis, and we're gonna look at a system where we have, what was that?
I thought that was X.
Oh.
I'm early for that. Come on now.
It's 10 o'clock.
Yeah, Josh is talking pretty big for a guy who woke up like 5 minutes ago.
Roasted.
Ouch.
That's okay, I did too.
Alright, as long as we all did.
Okay, so let's look at where we have a single H atom. And it's going to look like that. There's just one orbital. How many electrons are in that orbital?
1.
Yeah. Camera's like spazzing out.
Wait, why is there a O underneath it?
That is actually the
Oh, here we are.
orbital. Jeez. There we go. I want to go out further or closer. Let's see. There we go. This is actually the orbital itself.
Oh,
So it'll make more sense in a moment.
Oh, like it's the S orbital.
Yeah, this is just an s orbital. Now, if we have H2, what are the MOs we're going to get for H2?
it's gonna be the same, but it's gonna have 2 electrons.
Not
Or you say
quite.
the MO?
Yep, MOs.
Oh, so we'll have 2,
You have a
one a
bonding
little
and
bit
a
above,
bond.
one a little bit below.
Yep, one bonding and one anti-bonding, right? Remember,
Yep.
and what symbols do we give these guys?
Sigma star.
Yep. Okay, and how many electrons are in here?
2,
Yep.
0.
And 0 on that one. Okay, what does the wave function of this orbital look like? Like, do I have to color anything in here?
No.
No. What about for the anti-bonding one?
We'll
Are they in
color
the same
one
phase?
No.
out of phase.
Right. So this one should be colored in like that. Now, let's say we go to H3 and we're going to organize it like that. Okay. So we have 3 atomic orbitals. How many MOs do we need?
2.
3.
3. Remember, number of AOs has to equal number of MOs. So we get another one where they're all in phase. What other type of system can we have?
1's out of phase.
Yeah. So we could have one like this, where that one's out of phase. And then we actually have one where we introduce a node. And that node goes through that center one. And we get this. So we actually get 2 anti-bonding orbitals. And that makes sense because do we find H3 around at all?
No.
No.
Is there not the little hydrogen at the tip of that triangle?
Yep, at the tip of this one, there's no contribution from this hydrogen to the overall molecular orbital.
Okay, thank you.
Yeah, no problem. Now, how many electrons do we have?
2 in that one, and then
Yep.
1 at the top.
Yeah, and we'll just pick this one. It could easily be the other one, but we're just going with that. All right, now let's look at H4. So let's consider, we're going to organize it kind of in a circular chain, in a little square. And we get that guy, right? So we're going to have a bonding orbital, and note that this is a little bit lower in energy. Like they keep going lower in energy as we add more molecular orbitals. Now, give me another MO. Like, what's another MO going to look like for this H4?
That 2 are out of phase.
Yeah. So we could have,
Side or cross.
Just depends on how many nodes you want to.
like, we could have that guy, right?
Mm-hmm.
But this actually happens to be energetically equivalent.
Are you drawing those lower in energy on purpose?
Yes.
Okay.
But then we have a situation where these two are degenerate. They're the same in energy. So we got another one here and another one there. What about so how many MOs do we need for this system?
4.
4, yep. Actually, this one's meant to be degenerate, so we'll try and color that in. So what do you think the last orbital is going to look like?
Diagonal from each other.
Diagonal.
Would they be out of or probably some nodes?
So you get 2 nodes.
Yeah, you got 2 nodes.
Technically.
So we want this completely out of phase. Like that. Completely anti-bonding. An energy like this. Okay, so now when we start filling electrons, how many electrons do we need?
4.
1, 2, 3, 4. All right, now let's go to H6. We're going to try and draw these on the side. How many MOs are we going to get?
6.
Yep, 6. And it kind of looks like the pi system for benzene. So if we try to draw that out, we need a triangle, or a hexagon, excuse me, not a triangle. And we get one where they're all in phase that way. God, all the organic chemists are probably staring at my hexagons being like, those are awful.
None of them are here.
Watch Dr. B comes in. During a meeting. Hey guys, how's it going?
I would die.
So if we, for this MO, there's a node right along the center, and it's anti-bonding across that node. So this guy will have a node that bisects the benzene that way. And we get that. Next set. We're just going to keep introducing more nodes. And this one. Yeah. And this guy. Looks like this. And finally, this one I think you guys can describe to me.
Every other.
So what's it going to look like, John?
Just every other.
Yep.
Like
Every other one.
bond pattern.
Completely anti-bonding. Now, how many electrons do we need total in this system?
6.
Yeah. 1, 2, 3, 4, 5, 6. Okay. So that's pretty simple. Now let's ask the question, what happens if we build a 1D hydrogen chain? So everybody okay with that one?
Yep.
Yep.
Okay. So now, what if we move to a system where what we're going to do is we're going to have H infinite, infinite, where geez, I can't get level. There we go. Where we're going to have a bunch of H atoms, and they're going to be all connected in one another like that. And it goes on for infinity. That's the completely in phase situation. What happens is we get so many MOs, they just form a continuum where there's a bunch of occupied states along here, and there's a bunch of unoccupied states up top. So we represent this, instead of just writing all of those electronic states, we represent this with a band. And that's what that means. What's the 1D hydrogen chain going to look like for its molecular orbital up top up here?
Completely out of phase, I guess.
Yeah. So every other one's going to be colored in. And it'll look like this. So when we consider a band like this, we have the most bonding states. We have anti-bonding states. And what about in the center, where they're about the same energy as the 1s orbital?
mixed, or
Mhm.
that would be all out of phase.
Well, in that, oh, you mean like all out of phase? That would actually still be a bonding orbital. What about, so like, let's say we had a situation where,
Is it just non-bonding?
yep, non-bonding, that's exactly what I'm going for. Can you guys hear my cat out there? Cat really wants to come in, but I've locked her out.
Oh, let her in.
Let her in. My students say let her in, Lindsay. All right. Come here, cat. No, now she doesn't want to come in.
Don't be like that.
That sounds like a cat, right? No, it's okay. She's crying pathetically. So this is what our band looks like. All the bonding states are down here. Anti-bonding are up top. Non-bonding in the center. Okay, but this isn't quite rigorous enough. We can get a little more in depth in this. So we're gonna talk about this at length. Chemists tend to draw this type of picture where physicists draw something else. And what this something else is called, it's called a band structure, where you have an energy, you have something called a momentum vector, and a function that looks like this. And these two things, they actually mean the same thing. One is just something that physicists tend to use, and one's something that chemists tend to use. Now, we're going to talk about how do we get to this? Like, what does this picture mean? How do we get here? Okay. So the first thing we're going to do is we're going to start with the 1D hydrogen chain. The simplest system we can think of that's periodic. Okay. And what we're going to do is we're going to assume we have an infinitely long a 1D hydrogen chain. Whoa, missing an I. There we go. A chain which are evenly spaced, which the atoms are evenly spaced with a distance. Oh, I'm going off the screen. With a distance of A, so A is our lattice vector. We'll draw that out in a moment, between the atoms. So what our system looks like, we have a chain that goes on forever. And so on. And we're talking about this distance. And what did we say this distance was?
A.
Yep. That's going to be a distance of A. Now, what do we know about this chain? Could we ever get a chain like this, like at room temperature and pressure?
No.
No, what's going to happen to this chain?
Probably fold it.
H2.
Sorry, what was that?
It would break off into H2s.
Yeah, this chain would decompose into H2 at room temperature and pressure. However, at really high temperatures, you can actually squeeze this. They think they can make it stay kinetically stable, where you squeeze it at like gigapascals, terapascals, and this becomes a superconductor. So that would be pretty awesome if we could do that. We've made a really inexpensive superconductor. And we'll explain why today, that if we could metallize hydrogen like this, why it would be a superconductor. Okay, so before we get there though, we have to talk about something called block functions. Block functions. Which is, I don't know, sounds like a German way. It's like you're clearing your throat when you say the word. So there is a better way we can represent, there we go, jeez. There's a better way that we can represent our MOs and all the interactions of the atoms rather than just having a discrete set of MOs. So we're going to use these functions that state what the MOs look like, but in a mathematical form. So there's a better way to represent the interaction of all the atoms in the chain, rather than explicitly stating each of their MOs. The reason for this is because this system has a lot of translational symmetry. Due to translational. Okay. So we're going to look at our 1D chain, and we're going to pretend we start at the beginning of our 1D chain and let it move on. So if we label each atom with an index n, we're going to have each of our atoms in that chain. These are meant to be evenly spaced. These are each of our H atoms. And we're going to label their n, their index. This will be 0, 1, 2, 3, 4, and 5. Now, each of these atoms has a basis function or an orbital associated with it. We're going to label each orbital with a chi. So we have a chi sub 0, chi sub 1, chi sub 2, 3, 4, 5, and so on. So these things down here, they're known as the basis functions. But we can approximately think of them as the orbitals on our atoms. And what are the only types of orbitals we have here for our 1D hydrogen chain?
It would be 1s.
Yep, we only have one s. Okay. So now we need a periodic function to represent this information. So we need a periodic function to represent the wave function. Now in PChem, we've talked a lot about different functions that are periodic. Could you give me an example of a periodic function?
Sine.
Yep, sine. Give me another one.
What's the
Cosine.
Cosine. Yep. Okay. Give me another one.
E to the IKX.
What's that?
E to the IKX.
Yep. E to the IKX. And that's exactly the one we're going to go with. We're going to go with E to the IKX. So
Fancy.
Got e to the ikx, ika. In this case, our x is a. That's like the lattice, the distance between these two. Chi sub n. And now this is only for one chi sub n. So we need to do a summation across all of them.
Where you go?
Yeah. There,
Why is
shut the
fun?
door. Cats make more noise.
Where'd you-
No safe spot in this house away from that thing. Okay, so this is the function we have. So now let's ask the question, what happens when k is 0?
Does e go to 1 then?
Yep, so let's look at our function. We get k and e to the 0 like that, right? So what happens here?
It becomes 1.
Right, just like Maddie said and Josh said, this becomes 1. So if this basically just becomes this then, right? Now let's say we wrote out a couple terms. What are the, like, what's that gonna look like if we expand this sum?
It would just be x1 times x2.
Yeah, or plus, right?
Oh,
And so on, right?
Yeah.
Until we get to infinity. Okay, and I wrote psi sub k, but really we probably should have done psi sub 0 because it indicates what the value of k is at that point. Okay, so now let's ask the question, what do the MOs look like? For a k equal to 0. So these are each of our basis functions or orbitals, right? What do we know about the sign of these orbitals?
Positive.
So we can tell some information from this function, right? What's the sign between these orbitals?
positive? Is that
Yeah,
what you mean?
positive. What about between these two orbitals?
Positive as well.
Yep. Now let's say I was looking at this orbital and the one that has an index of 99. What's going to be the sign between them?
Positive.
Right. So if we draw this out, basically what we get is positive between each of these. But the way that it looks are all of these orbitals are in phase with one another. So what does this tell us? What type of orbital is this?
Bonding.
Yeah, it's a bonding orbital. So we just found a way to represent the bonding orbital of a periodic function that extends out to infinity using this equation. So now, let's look at another situation. We're going to ask the question, what about when k is equal to pi over a? Okay, so let's go back to our basis or our wave function. We got psi, and we'll indicate what our value of k is. We got pi over a. So we're going to have that same bit here E, what does this become up here?
IK pi,
We got I,
K pi.
K pi.
Oh,
Remember
wait,
we
no,
said,
just pi.
yep. I pi, and then we have one more thing up here.
Okay.
But don't the A's cancel out?
Yep, the A's go away. I, N. We should also get an N up here. Why is that N up there?
Great question.
Yeah, we'll see in a minute. Okay. Now, as we take this out, we get this as our summation. Now let's write out the first couple of terms of what this is going to look like. Pi sub 0 doesn't have a sign change. What's it going to look like for chi sub 1?
Negative.
Yep. Next, for chi sub 2,
Positive.
chi sub 3.
Negative.
Yep. And so on. It follows that pattern. Now let's ask, what do the MOs look like? Or K is equal to pi over A. So we've already established this is what the function looks like when it's expanded out. And so on. So let's try and draw that out. So what do I need to do to make it match this?
Fill in
Mhm.
that one and then the 3 one.
Yep. There you go. And what type of orbital is this?
Anti-bonding.
Yep. So this is an antibonding
Doctor.
orbital. Okay. Let's ask another question.
So many questions today.
I know. Too many questions. What about when K is equal to negative pi over A? Negative pi over A. We get summation n e to the negative pi I n.
Tired, John?
So this is what we get, which ends up actually being the exact same as our previous function.
So do we know where that N came from, or are we just adding it?
To make the mathematics work out, it has to be in there. I think actually I might have written the original function down wrong.
Okay.
Let's see.
So should it have been present in the K equals 0 equation?
Yes, I think it should have been present in the K is, well, yeah, in the K is equal to 0 equation. So back here, I think we should have had an N up here, which we forgot. And that would make more sense. Let me just double check to make sure that that's true though. Maybe. There we go. So let's see. Where are we? There we go. So let's see. Yep, there should have been an N in there. So back here, there should have been an N in that function. It doesn't really have much of an impact for this equation right here because everything's multiplied by 0, so it goes away. But in the other ones, it does have an impact. Okay, so what you can see is this function, it ends up being the exact same as our previous one. So if we write out the first couple of terms, we get chi 0 minus chi 1 plus chi 2 minus chi 3 plus and so on, right? So this is the exact same. Pi over a, the psi pi over a. Okay. So some things to talk about when we're discussing k. There are an infinite number of values. Of k. And k is actually a vector. It has to deal with something called reciprocal space, which we'll talk about in a little bit. Like, what does it mean? Basically, this is a relation to energy. It's a relation to momentum through a crystal. Right? But even though there are an infinite number of k's, there's only a set of unique values that you can get for psi, because we said this function is a periodic function. It's going to have a set of unique values. So there are only unique values.
What notation is that for the K in the one above? Is that K hat?
That's a k vector. It's meant to be like a half arrow.
Yeah, okay.
Kind of like that. Yep. And that just means it's a vector like you see in physics. So it has direction and magnitude. So the only unique values are for when the absolute value of k, or the magnitude of k, is less than or equal to pi over a. Other than that, you get the exact same function. And this range of the absolute value of k being less than or equal to pi over a is called the first Brillouin zone. So if you've ever read about solids and you've been really bored, you might have heard that term Brillouin zone, and that's what it means. Okay, now let's take these functions, let's start plotting them, let's get something graphical, and we can get some information out of this. So the next section, do babies first, band structure. Okay, so what we want to do, let's plot. Let us plot the energy E as a function of the wave vector, or that k vector. So if we plot that out, we have E on our y-axis. We have k, oops, on our x. and we're going to have a unique range. We're going to go from 0 to, what's the range that we're going to go to?
0 to A.
Not A. Where were we unique across our first Brillian zone?
Absolute value. So just be like,
Is it pi over A?
Yep, that's pi over A.
Chapter.
We're going to go from pi over to A. And the way this plot looks, it looks like this. Oh, maybe it focuses. There we go. So what's being described down here? Well, when we plotted our basis function, or when we plotted our molecular orbitals at 0, what type of interaction was it? Or what did our atomic orbitals look like?
They were all colored in.
Yeah, they were all colored in, or they were all blank, right?
Mhm.
What type of orbital is this?
Bonding.
Yeah. Now, when we plotted our function at pi over A,
Every other.
yep, it was every other, right? Because we had to have that sign change. So in this one, we had chi sub 0 plus chi sub 1, chi sub 2, chi sub 3. And this top one, we had a sign change between them. And what type of orbital, set of orbitals is this?
That would be anti-bonding.
Yep, anti-bonding. Okay. So now what we're going to do is we're going to plot this same function, but we're going to go, instead of just being from 0 to A, we're going to go to, or excuse me, from 0 to pi over A, we're going to go from 0 to 2 pi over A and see what it looks like. Am I okay to move this?
Yeah.
Yeah? All right.
Why is it called baby's first band structure?
I was trying to be funny, but no one thought it was a good joke.
I was like, is that a real term? Like, what?
oh, 100%, that's a real term.
Baby sounds
This is
great.
the band structure. All right.
Yeah. Don't worry. When I'm teaching my daughter all about like band structures and wave theory.
That's only like 6
Wild.
months.
Yeah. Kid never had a chance in hell. Right out of the gate.
He's gonna be such a nerd.
Oh yeah. Good time.
Life's easier that way.
I'll have to take her over to my brother's house so she can learn how to like actually throw a ball or do any of that. So let's plot from 0 to 2 pi over A. See what we get. So again, we'll have our energy along here. Whoa, come on, focus. There we go. We have our K vector here, and there are some points that we're going to draw. We got 0 right in the center where I put that K. It's where I wanted pi over A. And then we'll have 2 pi over A. Okay. The distance between these should be the same, but because of where I put my K, it doesn't work that way. We've already drawn what this looks like. Somebody show me what it looks like with their hands.
Double it up.
Double it up.
Stack the one on top of it.
So it looks like that, and then what's going to be the rest?
No,
The same thing again, like a repetition.
yeah, I thought it'd keep going up, but I'm guessing
So
it's going back
I just
down.
keep going up like that.
So I
No,
thought,
it probably goes down to the same energy level.
Yep.
No, it doesn't?
oh, it's periodic. Yeah.
Yep. What's this? This is like a sine function, right? So it's periodic. Now let's say we extended it out even further. we went to, I don't know, let's see, 3 pi over a. What's it going to look like?
The same.
What's going to happen?
It's gonna go up.
Yep, it's going to go up and it's going to look like that first area. So this area is called the first Brillouin zone. What do you think this one's called?
The second.
Yeah, exactly. Not very creative, right? And then we got the third.
Oh, I thought it was the fourth.
Man, if there were ever jokes about Brillouin zones, this would be the class for it.
I just miss Coov and Duve.
They'll come back. Don't worry.
Oh Jesus.
Oh, God.
Yeah, don't miss them too much.
All I think about is Coov and Duve.
We should get team shirts or something. Team Coov, Team Duve. So I've been kind of dodging the question of what is this thing called K. All right, so let's talk about that really quick. What is K? Well, K is an index that labels which irreducible representation of the translation or translational group, your wave function transforms. And with one single sentence, I found a way to make this even more confusing. So, what do you know about irreducible representations? What do they keep track of? Like, what's the point of them? What are they looking at?
All the movement of a molecule can have.
Yep, it's keeping track of the movement of atoms. Specifically, what about that movement of atoms? Like, where did we have to start to get those irreducible representations? What's the first thing you have to do?
The reducible.
Yeah, you got to get the reducible. Even before that, what do you have to do before you get the reducible?
Got another point group, and then you got to look at the character.
So point groups, when we're talking about point groups, what are we really discussing?
The symmetry.
Yeah.
Planes of symmetry.
Yeah, the symmetry. So what this is saying is the K vector keeps track of the symmetry of those set of molecular or atomic orbitals. What we're really saying here, we're talking about symmetry. Okay. The other thing, K contains the number of nodes in your system. It counts the nodes. The other thing is it's a wave vector that measures the momentum of a wave traveling through this periodic system, and it's related to energy. It's also a wave vector which measures momentum, and as we know, momentum is related to energy. Okay. So K is equal to 2 pi over lambda. And we know that lambda is equal to Planck's constant divided by momentum. And this relationship here comes from the de Broglie relationship. Whoa, I forgot his name. De Broglie. Where do you remember what the de Broglie relationship said? Like maybe in, what was that?
Not really. No.
Yeah.
All right, hold an Anna. Drop something metal. What the de Broglie relationship stated was is everything in motion it can be described as a wave.
Oh, yeah.
Okay. So that's what that wave vector is. It's a measure of all of these things. To really get into the true nitty-gritty details of what it is, we have to talk about something called reciprocal space, which we're going to dodge for a little bit. Reciprocal space is kind of confusing because the further you move, the shorter in reciprocal space it is. And this comes from actually identifying crystal structures and shooting electron beams and neutrons at these crystals. So let's go back to the band structure thing. We have plots that look like this, but we're going to ask a couple questions. I know, more questions, right?
Always.
First thing we're going to ask is how many lines are there? How many lines are there? As many orbitals as there are in a unit cell is equal to the number of lines. Each line
I can't see anything.
oh, sorry. Each line is a, geez, God thing. Quit spazzing out. There we go. So the number of lines that we draw have to deal with how many orbitals are in the unit cell. So in our unit cell, how many orbitals were contained? And what was the orbital? So how many orbitals did we have back for our 1D hydrogen chain?
Isn't it infinity?
It does go to infinity, but we're considering this system, right?
So is 1s.
Yep, just 1s, because if you look, that's our unit cell. That's how much we said is unique, and we're looking across it that way. And there's only one total atom in there. And there's only one S in there. That's why we drew only one line for what we have. So each line is a band generated by a single orbital. Okay. So I also said that these are related to MO diagrams. In MO diagrams, we really care about where the electrons are. If we look back at this plot, or I don't know, even this guy, I don't see where there are any electrons in this system at all. So we're going to ask the question, where are the electrons? Okay, first thing is each band, each of those lines that's drawn, each band can accommodate the same number of electrons as a single atomic orbital. So how many electrons can a single atomic orbital hold?
Doesn't it depend?
So like, how many electrons can a 1s hold?
2.
2. How about a 2px?
2p would be
So
6.
there's still 2.
Well, I said 2px, a specific one.
2.
Yep, 2. What about, I don't know, a dz squared orbital?
4? No.
What was that, Josh?
8.
Remember,
Oh, wait.
So there's
no, it's
2, because
4.
we're just talking about very specific.
yep, it's still just 2 because we're talking about a very specific orbital. So each one can only hold 2 electrons. How many electrons do we have, though? Well, the number of electrons is equal to the number of electrons in the unit cell. And finally, the Fermi level. Which we shorten to E sub F like that. It keeps track.
Sorry.
That's okay.
I'm still in Allegheny.
Yeah, I was about to say, I'm pretty sure you hear that from mine too.
If you get on top of the hill near my house, you can hear it. Actually, so my grandmother lived right in town, and whenever I'd spend the night over there, the train would wake me up at like,
Oh, yeah.
I hate it.
oh, she'd sleep right through it, no problem. I was like, how? Well, the Fermi level keeps track of what portion of the band is occupied and what portion is unoccupied. Okay, so what we're going to do, we're going to draw our 1D hydrogen chain again, the band structure of that guy. Example, 1D H chain. Okay, what's the region that we want to go to for a band structure, for a 1D hydrogen chain? What unique values are we doing for K? Where do we start?
1, 0. Start at
0, yep, and we're going to what?
Pi over A?
A.
Or are we doing 2 pi over A?
Yep, pi over A. And we've already drawn this out. And it looks like that, right? Okay, now we have to indicate the Fermi level here. Where are we going to draw the Fermi level? Let's first go back to our system, what it looks like. And each of these regions, they're a distance of A apart from one another. How many atoms are in the unit cell?
2.
2.
Like full number of atoms.
Oh, okay. I guess 1.
Yep, 1 because we got a half of this first one, half of that guy for a total of 1. So we have 1 hydrogen atom contained in our unit cell. How many electrons do we have then in our band structure?
1.
1. Okay, so we got 1 in here. Where are we going to put that Fermi level?
Let's say right in the middle.
Right in the middle? Yep, that's exactly right, because how many electrons are contained in this band? Maximum, how many can it hold?
2.
2. Yep. So the Fermi level, actually I'll do it in red.
Me too.
Hey, great minds think alike. So there's our Fermi level. And it's cut up halfway because This portion down here, this portion's occupied. What about this top part?
Unoccupied.
Yep, unoccupied. I think I need 2 P's though.
No.
Nope, I was right.
No, just one P.
Whoops. There we go. We're better now. And now if we try and draw that like in the way we first started. That's what our band looks like. Okay, so let's write that down. Just that we have 1 electron in our unit cell. Therefore, the band is half filled. Okay. Oops. Everybody okay with me moving that?
Mm-hmm.
Okay. So next question, how do we know the steepness of the band? Keep punching the camera. There we go. So how do we know the steepness of the band? The steepness, it's basically the difference between the bonding and the anti-bonding level, right? That's what we're talking about here. What controlled the distance between the bonding and anti-bonding orbitals for a molecular system? So if we had an MO, I don't know, let's look at just a simple H2 atom. What controls the distance between this orbital and that orbital? Do you remember?
Isn't it like the bond length?
Yep, the bond length, right? So we're talking about bond lengths. We're talking about how much these orbitals are actually, or atomic orbitals are overlapping with one. So the quality of overlap is what we're looking at. So the quality of overlap between atomic orbitals dictates what is called band dispersion. And what this really is the steepness, i.e., there we go, the steepness. And like Josh said, what controlled that, Josh?
Bond length.
Yep, the bond length. So the bond length controls this. Now, another thing, this steepness is sometimes called the band width also. Okay, and dispersion is the difference between the top and the bottom band of the band. So dispersion is the measure between the top and the bottom of the band. So what we're going to do is we're going to look at 3 systems. So let's consider our 1DH chain where A is equal to 3, 2, and 1 angstrom. So we're basically increasing that unit cell size. We're increasing the distance between each of those atoms. So we'll have our A is equal to 3 angstrom system, let A is equal to 2 angstrom system, and A is equal to 1 angstrom system. And we're going to have 3 plots, the same plot, E, K, and we're going from 0 to pi over A in each of these.
Wait, it was pi over a and now it's a over pi?
Oh, sorry. Dyslexic. Vertically dyslexic, I guess. There we go. Okay. We need K here. All right. A lot to scramble down. Sorry, guys. Okay. So now, the system that we drew previously, the bond length we said was around 1 angstrom. So this will look approximately the same. And where's our Fermi level for this system?
In the middle.
Yep, right in the middle. Okay, what's going to happen as we go to 2 angstroms? Our atoms are getting further away. What's going to happen to the quality of the overlap?
It's gonna get worse.
Yep, it's going to get worse.
Spread out more.
Yep. But what'd you say, Josh, for that last bit?
It'll spread out more. So like the top and bottom energy values, will that disperse more?
That's if the quality of overlap gets better, they spread out further.
Oh,
right?
so it'll get closer together then.
Yep, exactly. So we're going to try to stay around that Fermi level. That Fermi level is going to be the same. But this dispersion is going to go like that. Sound like someone shooting off fireworks or something. What about for this system? What's that going to look like?
Probably being smaller.
Almost a line.
Yeah, almost a line. It'll look kind of like that. Really tiny. So you can see the quality of overlap makes a big deal. Okay. Let's look at an example. We're going to ask the question, how much time do we have left, by the way?
3 minutes.
3 minutes?
Mm-hmm.
Okay. My phone didn't go off yet. Oh, there it goes.
I missed that yesterday.
We all did.
Yeah.
Got me up at night.
What does the band structure for a 1DH chain look like where the lattice vector, that A, is infinitely long? So we're going to plot the same junk we always do. We got K, we got E, we're going from 0 to pi over A, make Tara happy.
Yeah.
Oh,
what's it going to look like for this system where we have an infinitely long distance between each of our H atoms?
Would it be a straight line?
This makes
Yeah,
Fermi
straight
level.
line. And where's the Fermi level?
There.
On that one.
Same.
Yeah. Okay. So next time, what we're going to do, we're going to move on into more complicated systems. We're going to check out where we start talking about p orbitals, and we're going to look at which way do the bands run. Okay. I'll be posting the assignment up on Moodle, and I will hopefully be going in today to scan your guys' exams and get them back to you. Okay.
You can keep
Are
them.
there are there any questions about anything we talked about?